to part 2 of the photoelectric effect. Last video we talked about some of the important properties of the photoelectric effect. So just to recap, number 1 was that the electrons are emitted instantaneously. 2 said that there is a minimum frequency which we call the threshold frequency, F0, and below this frequency no electrons are ejected. 3 said that the intensity of light affects the number of electrons emitted, not the energy of those emitted. And 4 said that the electrons are emitted from the material with a range of frequencies. These range from 0 to a maximum. So what's the problem with waves if we consider these characteristics of the photoelectric effect? Firstly, number 1, the intensity or the brightness of light is proportional to the amplitude and hence the energy of radiation. Light with a greater intensity should emit electrons with a greater kinetic energy. However, this was not the case in the photoelectric effect, as more electrons are emitted and their kinetic energy depends on the frequency of light. According to the wave theory, if we increase the frequency of the light, this should increase the number of waves striking the metal surface per second. Therefore, more electrons should be ejected. This is also not the case. The electrons are ejected with a greater kinetic energy, rather than more electrons. So Einstein had an explanation for this. He said that light does not consist of a continuous wave. It consists of packets of waves called photons. Each photon has an energy of E equals hf, as we saw earlier, where h is Planck's constant of 6.6 times 10 to the negative 34 joule seconds. And photons have some wave properties and some particle properties, depending on the situation, which sounds a little bit hand-wavy, but it checks out. Each photon will be absorbed by one electron. That was his explanation to justify this, that each photon absorbed by one electron. The work function then, which we use capital W, is a property of the material, and it's the minimum energy required to remove an electron from it. So it's like when we talked about the threshold frequency, it's the minimum frequency required. The work function is how much energy we actually need to remove an electron. So if we look at this diagram here, an electron is bound to the material and it requires an energy to make it leave. So we talk about it as negative energies. To remove an electron, its energy level has to be raised to 0 because it's bound. So it's almost like it's embedded within the thing. So we need to raise it up to this 0 point, and from there it can escape. So for example, copper has negative 4.7 electron volts. That is its energy. So Einstein said that photons behave like a particle. When an electron in the metal absorbs the energy of a photon, this transfer of energy is immediate, and the electrons are emitted instantaneously as long as the photons have enough energy to meet the work function requirement. So instantly the photon is absorbed by the electron. We need the right energy amount to actually raise it to that 0 level from its negative energy, which is the work function. And if we do that, then instantaneously that electron leaves its object, its particle, its shell, whatever, and it's ejected. In the second rule, if the frequency of light is reduced, the energy is reduced, using that E equals hf formula. So when the energy drops below that work function, the incident photons do not have enough energy to release the least bound electrons. So no electrons are emitted. This is where the threshold frequency comes in. The work function is given by W equals hf0. So the work function, as we talked about earlier, Planck's constant, as we've seen a million times now, and f0 is our threshold frequency. 3. The intensity or brightness of the light is directly proportional to the number of photons in the light. This means that there are more photons available to be absorbed, and this explains why more electrons are emitted with more intense light. Exactly as I said earlier, it's directly proportional to the number of photons. So an intense light, or bright intensity, means lots of photons. Lots of photons means lots of electrons ejected. 4. If using the law of conservation of energy, part of the energy of the incident photon may be used to release an electron. The rest becomes its kinetic energy. since the electrons that are deeper in the metal require more energy to be released, the amount of kinetic energy that's available varies. So depending on how deep those electrons are, they're going to consume different levels of energy to actually get out. So when they do get out, they end up with this band or this range of kinetic energies available. Anything from the surface is emitted with a much greater kinetic energy because it didn't take as much energy to get it out than something deeper within the surface. This means that the electrons are emitted with a range of kinetic energies up to a maximum value. The maximum value is obviously going to be the closest electron to the surface because it takes the smallest amount of energy, and therefore it'll be easily kicked out and have the most amount of kinetic energy when it leaves. You can't have any more than that because there are no electrons closer to the surface than that one. If we increase the frequency of the incident light, this increases the energy of the incident photons, and therefore the maximum kinetic energy of the electrons. So the frequency is then affecting the kinetic energy. The least bound, or the closest to the surface electrons, are released with the greatest amount of kinetic energy, and we will call that EK max. So the maximum kinetic energy released is released by the least bound, or the closest to the surface electrons. So EK max is the notation that we use for this. The energy of the photon is used to release the electron, and the remaining energy becomes this kinetic energy. Therefore, the energy needed to release the least bound electron is the work function W. So we've got the energy of the photon, that then equals the energy to release it plus the energy maximum, the EK max. Energy of the photon was HF. The release energy is the work function, so how much it takes to get it out is the work function, and EK max is just the maximum kinetic energy available. So then if we just rearrange for the maximum kinetic energy, we find that the maximum kinetic energy that we can obtain from an electron for that material is HF, so Planck's constant, the frequency minus the work function. So looking at that, the Kmax, or EK max depending on how you write it, it's the HF minus W. If you compare this equation to that of a straight line, so y equals mx plus c, you can actually see that in this case Kmax is the y value, h is the slope of the line, f is the variable because we're changing the frequency of light in this situation, and the negative w is the y-intercept to say that it crosses at minus w. So if we plot this, we end up with graphs that look like this. You can see your x variable, your f's. You can see your work functions, which are your y-intercepts down here in the negative, and the slope is Planck's constant in this case. So this is actually quite an interesting comparison mathematically from the maximum kinetic energy obtainable to the equation of a line. And we can use the mathematics to predict results by plugging in these values. If we know some of them, we can graph it to find a solution. So have a go at these questions. Using the photoelectric effect, visible light, minimum frequency is given, state the threshold frequency, calculate the work function using that formula we've just seen, and then if we've got a metal, it's illuminated with a wavelength that we're given, 200 nanometers, calculate what the Kmax is for the emitted electrons. So I'll give you a minute to work through that. As usual, pause if you need more time, and we'll go through the answers in 1 minute. So threshold frequency of the metal, 6.2 times 10 to the 14 hertz. Work function, we use the HF naught. We plug in our 6.63 times 10 to the negative 34, Planck's constant. F naught from part A, we get our 4.1 times 10 to the negative 19 joules. So that is how much energy is required to get it to the surface, to escape its material. Then in this situation, we're given the wavelength, we want the kinetic energy, I need V, I use my V equals F lambda, I rearrange to find the frequency, plug that in, I get my frequency, I then plug that back into my EK max formula. HF I now know because I know frequency, work function I found earlier, plug it all in, crunch some numbers, I get 5.8 times 10 to the negative 19 joules. So that is the maximum kinetic energy that the electrons emitted will have. Part 2. We've given the work function of silver, calculate the threshold frequency for it. Then we've got frequency of light illuminates the silver, calculate K max, so same sort of style. Calculate the speed of the electrons emitted with the maximum kinetic energy. And then again in 3, sodium, you're given the work function, they ask you to show that the frequency of light will not eject electrons from it. So it's a slightly different one in 3 because they're showing that this is not ejecting electrons. So basically what you want to show is that this is not enough to obtain the work function. So in this case, just pause the video now if you want to have a go at these. Otherwise, I'm just going to go through them because they're very similar to what we saw before, and the concepts are fairly repetitive. So I'm just going to reveal these straight away. So in this case, again, plugged in the values, we've got the work function and the threshold frequency. 1.14 times 10 to the 15 hertz is our threshold frequency. So that's the frequency that we need in order to obtain the ejected particles. Because remember, the frequency is linked to the energy of the particle, which then translates to having enough energy to eject the electrons. EK max is the HF minus W formula. Plug in our values, we get 1.6 times 10 to the negative 18. Then if we want the speed, we plug in our traditional kinetic energy formula, because they're convertible, that is just the kinetic energy, half mv squared. We rearrange because we want V, so we've got EK over M, 9.11 times 10 to the negative 31 is our mass, and we get 1.87 times 10 to the 6 meters per second. So these masses and things will be given to you on your formula sheets if you need it. Sodium, work functions given, show that it'll not eject electrons. You want to use the work function formula. We know the frequency, so we plug that in, we get a range there. And therefore they've said that the frequency is lower than the threshold frequency that we've found, the threshold frequency below which no electrons are emitted. So we've basically just shown this is lower than the threshold frequency needed to actually eject the electrons. Therefore, nothing will be ejected. That's what they're looking for. So the next part is the maximum energy experiment. So the maximum energy of an emitted electron can be determined experimentally. A photoelectric cell is placed within a circuit, which we've looked at earlier. So the photoelectric cell is this vacuated container with the emitter and the collector, or the anode and the cathode, and it's hooked up to a circuit. White light that's been passed through a filter or light of a single frequency is used to illuminate the cathode. A negative potential is applied to the anode, which produces an electric field which repels the electrons and stops them from reaching it. So it's kind of like, if you think of a Star Wars analogy, it's like generating an electric force field around this anode so that the electrons don't reach it. Sorry, I should have said this bit. So it protects the electrons from getting to it. Then we increase the potential difference, making the anode increasingly more negative to repel those electrons. Very few electrons have enough kinetic energy to overcome that and actually get into the circuit to reach that anode. So that when we eventually find that no electrons are reaching the anode, the current will drop to zero, and we refer to this as the stopping voltage. So we basically take the standard experiment where we would normally be generating a current by these electrons reaching the anode. We generate an electromagnetic or electric field around this object to stop the electrons, to repel them, but some are still getting through because they have enough energy to overcome that electric field, reach the anode, and then run through the circuit, so we've still got some current. we increase that potential difference so that the field is stronger, less and less electrons get through, and we keep increasing until nothing can overcome that point. Then the current drops to zero, and that is our stopping voltage. So it's the voltage at which no electrons can overcome that resistance. Why is that useful though? That seems kind of pointless. However, if we do that, we can then use that to calculate what the actual energy of those electrons being ejected was by relating it to the potential difference or the electric field strength that we actually had to generate to overcome. So when we achieve this stopping voltage, the work done by the electric field is equal to the maximum kinetic energy of the emitted electron, because they're cancelling each other out. So they're equal and opposite, no current flows. So we could say that the work function here, or the work done, which is Q delta V from our earlier electric field stuff, is equal to EVS, or V voltage stopping voltage. That's then equal to the kinetic energy maximum. So we can then say that the maximum kinetic energy of the emitted electrons is given by this EVS. So the stopping voltage times the charge of the electron. The color of the filter is then changed, and the new stopping voltage is used to calculate the EK max for other frequencies of incident light. So we do the same thing, we dial back the stopping voltage, change the filter so we've got a different color of light, different frequency, repeat the experiment. We then graph this kinetic energy max, the EK max, against frequency. And since from before we said that EK max equals HF minus W, we expect and we end up seeing that we get a linear relationship, but we don't expect it to pass through the origin because we know that this negative W, the work function, shifts it below the x-axis. So we should have this negative intercept point. When we analyze the graph of this EK max against frequency, and given that EK max is HF minus W, the slope gives us Planck's constant, the y-intercept gives us the work function, and the horizontal axis intercept gives us the threshold frequency. So just as we saw before in the earlier video, I explained that this is a linear formula, so we expected that. Now that we know that, we can use that experimentally to calculate this using that stopping voltage. So what could you conclude about the two metals that are shown below? We've got metal 1, metal 2. In this case, you can see that this metal has a higher threshold frequency. The gradients of both lines are the same, and we would expect that because this is just Planck's constant. So if they're not, that suggests some sort of error within the experiment. But if they are, then that's good. That confirms that we're getting Planck's constant or close to it for the gradients. Metal 2 has a higher work function. And when we say higher work function, it's because if you think of it, it's deeper below the surface. It's a higher, larger negative number. It takes more energy to get it up than this one does. So an example question. Using this graph, state the threshold frequency, the work function, calculate the gradient, and justify why it represents Planck's constant, and calculate the percentage error. So these are a great example of an experimental style question. So the test that we've got coming up soon on experimental skills, this is a great example. Calculating gradients, percentage errors, things like that. The first two parts are just linked to what we've talked about so far. So as usual, 1 minute, give it a go.
What would you do if you were asked to give up your dreams for freedom? What would you do if asked to make the ultimate sacrifice? Would you think about all them people who gave up everything they had? Would you think about all them war vets, and would you start to feel bad? Freedom isn't free. It costs folks like you and me. And if we don't all chip in, we'll never pay that bill. Freedom isn't free. No, there's a hefty...
Alright, so looking at the threshold frequency It's the horizontal axis intercept, so it's around the 3.8 times 10 to the 14. Work function is the vertical, the maximum kinetic energy axis intercept. So W is around the 2.4 times 10 to the negative 19. Calculate the gradient, plain old rise over run from whatever values you want to use. 6.2 or thereabouts times 10 to the negative 34 joules per second. And it says justify why it represents Planck's constant. So you could talk about that formula, the EK max formula. W represents that plus C for the y-intercept. M represents the slope. And given that M is h in this equation, the h gives us Planck's constant, which is what we were calculating using that gradient. Calculate percentage error. Percentage error in this case is 6.5%. So it's pretty close. When you think about that accuracy, 6.5% is a pretty good result. So in summary, for this photoelectric concept, light behaves like particles, which when we say light is a particle, we're talking about photons. That is the particle. It has energy, E equals hf, and it has momentum, P equals h divided by f. You're expected to be able to calculate the energy and the momentum of the photon in various regions of the electromagnetic spectrum, so different frequencies, etc. When light of a high frequency hits things, it can be absorbed. When it's absorbed, electrons are emitted. This is the photoelectric effect. The intensity of the light affects the number, but not the energy of the emitted electrons. The minimum frequency, the F0, is the point at which electrons are emitted, and it varies with the type of material, and we also call that the threshold frequency. So F0, threshold frequency. The work function, capital W, is the work function of the surface. It's the minimum energy required to remove an electron from it. So again, it's dependent on the material, but it's how much energy we need to get it from this below the surface, so to speak, to the ejection point. Work function is related to the threshold frequency by W equals hf0. You're expected to describe an experimental method for investigating the relationship between the maximum kinetic energy of the electrons calculated from the measured stopping voltage. So that's using that stopping voltage equation that we talked about. EK max is E times voltage S, or stopping voltage, and the frequency of light incident on the metal surface. So just as we talked about in this video. Describe how Einstein used the concept of photons and the conservation of energy to explain the experimental observations of the photoelectric effect. So at the start of this video I talked about those justifications, why they behave that way. You're just expected to be able to explain that in your words. Plot experimental values of maximum kinetic energy versus frequency, and relate the slope axis intercepts to that formula, exactly like we just saw in that question. And lastly, solve problems that require that EK max equals hf minus W. So this is the expected outcome and understanding for the photoelectric concepts.